The Willow quantum computing chip from Alphabet represents a significant leap in quantum technology. By utilizing qubits in a weak noise phase, where qubits are more stable and less affected by external disturbances, Willow performs computations far beyond the capability of classical supercomputers, which process data sequentially. A key achievement is its success with random circuit sampling, or RCS, which is a quantum benchmark designed to test a quantum processor's ability to handle complex, high-dimensional problems. Willow demonstrated its superiority by completing a task in under 5 minutes that would take a classical supercomputer around 10 to the power of 25 years. This breakthrough places Alphabet ahead of its competitors like NVIDIA, showing the potential of quantum computing to revolutionize AI and large-scale data modeling. Now let's take a step back and understand what classical computers are doing under the hood, what a qubit is, and what concepts like superposition and entanglement are. Classical computing uses bits, which are binary units of data that can be either 0 or 1. These bits are processed through transistors, tiny electronic switches that control the flow of electrical signals. With millions or even billions of transistors in modern computers, they execute a variety of logical operations efficiently. Quantum computing, on the other hand, uses qubits or quantum bits. Unlike classical bits, qubits can exist in a state of 0, 1, or both at the same time. This means quantum computers can process far more information simultaneously compared to classical systems. Now let's talk about some quantum mechanics like superposition, entanglement, and qubits. In superposition, a qubit can be in a superposition of states, where it is in a combination of both 0 and 1. This allows quantum computers to explore many possible solutions simultaneously rather than one at a time, which is a key factor in their potential for speedup. When qubits are entangled, the state of one qubit becomes linked to the state of another, regardless of the distance between them. And this linkage means that the measurement of one qubit instantly affects the state of the other. Entanglement helps achieve quantum speedup because it allows quantum computers to process and correlate large amounts of data in parallel. In classical computing, you need to process each possible solution individually, but in quantum computing, entanglement allows qubits to work together, processing many possibilities at once. This exponential scaling of computational resources can provide a dramatic speedup for certain types of algorithms, such as factorization using Shor's algorithm and unstructured search using Grover's algorithm. Qubits are the basic unit of quantum information. They can be realized with various physical systems, such as superconducting circuits, trapped ions, or photons. Each physical realization has its strengths and challenges, particularly in terms of coherence times and error rates. Okay, but you may not be familiar with coherence time, decoherence, and error rates. Let's break that down. Quantum systems are highly sensitive to their environment. This sensitivity leads to decoherence, a process by which qubits lose their quantum properties and behave more classically. Coherence time refers to how long a qubit can maintain its quantum state before decoherence occurs. Longer coherence times are essential for performing quantum operations accurately. Early quantum computers had very short-lived coherence times, which limited the number of operations that could be done in a single run. And coherence is essential because quantum information is carried in superposition states which rely on precise alignment of phase and amplitude. And qubits maintaining their quantum state involves maintaining this phase relationship over time. The TLDR here is that coherence ensures that qubits can retain their quantum properties long enough to complete calculations. If we loop back to the weak noise phase in Willow's design, what this is doing is that it's enhancing coherence by minimizing the impact of external disturbances that typically cause decoherence. And this means that qubits remain stable for longer periods, reducing errors in computations. So the important thing to note here is that as qubits interact with their environment, they begin to lose their quantum state. This happens due to noise or unwanted interaction, which is why error correction techniques and hardware improvements are so important for quantum computing progress. Let's remember that quantum computers rely on physical qubits, which are the actual quantum hardware that performs the operations. However, due to the fragile nature of quantum states, a single physical qubit is often prone to errors and decoherence. To counter this, Google is forming a single logical qubit from multiple physical qubits. And a logical qubit is a stable qubit that represents quantum information more reliably, thanks to error correction codes. And now we can explore a completely different rabbit hole of error correction codes and surface codes in quantum computing. Error correction is pivotal in quantum computing due to the fragile nature of qubits. They're highly susceptible to noise, decoherence, and operational errors. Unlike classical error correction, which can simply duplicate bits, quantum error correction must preserve the delicate superposition and entanglement of qubits. Surface codes are one of the most widely used error correction methods. They work by arranging physical qubits in a 2D grid and using additional ancilla qubits to detect and correct errors. Instead of tracking individual qubit errors, surface codes identify syndrome measurements, which reveal where errors have occurred without disturbing the quantum state. This approach allows logical qubits, which are the error-corrected qubits, to be constructed from multiple physical qubits. Surface codes are effective because they can correct both bit flip and phase flip errors, two of the most common types of errors in quantum errors. And let me briefly describe these two types of errors. A bit flip error occurs when a qubit state flips from 0 to 1 or vice versa, similar to a classical bit flip. For example, if a qubit is in state 0, but noise causes it to switch to 1, it leads to incorrect computation. Unlike a bit flip, a phase flip error changes the phase of a qubit's superposition. If a qubit is in state 0 plus 1 over square root 2, and it's hit with a phase flip, it becomes 0 minus 1 over square root 2. The amplitude of the state remains the same, but their relative sign changes, which disrupts quantum interference. Both types of errors can distort quantum algorithms, so error correction methods like surface codes are designed to detect and correct them without measuring the qubit's actual state, which preserves quantum coherence. By leveraging advanced error correction techniques and optimizing qubit fidelity, Willow achieves logical error rates as low as 0.0001 per operation, making it far more reliable than earlier quantum processors such as Sycamore in 2019. Now let's talk about the key improvements of Google's Willow chip. Willow employs quantum error correction techniques using surface codes, and surface codes work by encoding a single logical qubit into multiple physical qubits, often dozens. And this allows the system to detect and correct errors that occur during quantum operations. This encoding significantly reduces the impact of environmental noise and operational imperfections. There's also an increase in qubit stability and coherence times. Willow uses superconducting qubits arranged in a 2D grid architecture. This layout, combined with enhancements in fabrication techniques and noise isolation, leads to improved qubit stability. And stability is crucial since unstable qubits are prone to decoherence, which disrupts computations. Remember that coherence time refers to how long a qubit can maintain its quantum state before losing information due to environmental interactions, or decoherence. Willow achieves coherence times of up to 98 microseconds, a substantial increase from Sycamore's coherence time of around 10 to 20 microseconds. This 5x increase allows more quantum gates to be executed before decoherence affects the results. There's also a massive increase in scalability and quantum volume. Willow contains 105 physical qubits, up from Sycamore's 54 physical qubits. While raw qubit count is not the only measure of quantum performance, it indicates Google's growing ability to build larger, more complex chips capable of supporting larger quantum workloads. And then there's also quantum volume, which is a measure that captures a quantum computer's overall computational power, factoring in qubit count, gate fidelity, connectivity, and error rates. While Google's official quantum volume number for Willow has not been disclosed, this improvement in error correction, coherence time, and qubit count suggests a substantial increase. How about gate fidelity? Okay, before I talk about gate fidelity, let's give you an introduction to quantum gates. Quantum gates are the fundamental operations performed on qubits. Unlike classical logic gates that operate on binary zeros and ones, quantum gates manipulate qubits in superposition, enabling them to perform multiple calculations at once. Some examples include Hadamard, Poly-X, and CNOT gates, which are crucial for entanglement and quantum logic. Gate fidelity refers to the precision with which quantum gates or operations are executed. Willow improves gate fidelity significantly with single qubit gate errors of 0.035% and 2 qubit gate errors of 0.33%. By comparison, Sycamore's gate errors were much higher, leading to more noise in quantum computations. Higher fidelity allows for deeper circuits and longer computations without the need for frequent error correction. The Willow chip also has an average of 3.47 connections per qubit, which means that qubits are not fully entangled with every other qubit, but maintain sufficient connectivity for efficient computation. Now, the most important metric of all is the benchmarking speed and computational efficiency. Willow's performance was evaluated using the random circuit sampling, or RCS benchmark, and this benchmark measures how well a quantum processor can sample complex quantum circuits, a task that is extremely difficult for classical supercomputers. RCS involves generating and verifying outputs from random quantum circuits, and Willow was able to complete an RCS task in under 5 minutes, compared to the fastest classical supercomputers, which would require an estimated of 10 to the power of 25 years to perform the same task. The performance improvement from Sycamore in 2019, which was Google's last iteration of the quantum AI chip, to Willow is not just incremental, it's straight up exponential. Google's earlier claim of quantum supremacy with Sycamore pales in comparison. Sycamore was a 54-qubit quantum computer which was able to solve a problem in 200 seconds that would take a classical supercomputer 10,000 years. Willow truly pushes this boundary further. If you learned something new in this video, please give this video a like and comment down below any outstanding questions. And if you would like to stay tuned for future videos, please hit the subscribe button below as well. As always, thank you very much for watching this video, and happy coding!